Welcome to Chapter 9, where we'll dive into the fascinating world of statistics. This chapter will equip you with essential tools for analyzing and interpreting data effectively. Statistics is everywhere around us, from analyzing business performance to understanding scientific research, from sports analytics to social media trends. Let's explore what makes data analysis so powerful. In this chapter, we'll cover three essential areas of statistics. First, we'll revise fundamental statistical concepts like measures of central tendency and variability. Second, we'll explore curve-fitting techniques, learning how to model data relationships and make predictions using mathematical functions. Finally, we'll dive into correlation analysis, discovering how to measure and interpret relationships between different variables in your data. Here's a preview of correlation analysis. You'll learn to interpret different types of relationships between variables, from perfect positive correlation to no correlation at all. By the end of this chapter, you'll have the skills to analyze data patterns, fit mathematical models to real-world data, and understand the relationships that drive decision-making in science, business, and everyday life. Let's start with a quick revision of fundamental statistical concepts that form the foundation of statistical analysis. We'll review measures of central tendency, which tell us about the center of our data, and measures of dispersion, which tell us how spread out our data is. Measures of central tendency help us find the center or typical value of a dataset. Let's use this sample dataset to demonstrate the three main measures. The mean is the arithmetic average. We add all values and divide by the number of values. For our data, the mean is 6.57. The median is the middle value when data is arranged in order. With 7 values, the median is the fourth value, which is 6. The mode is the most frequently occurring value. In our dataset, the value 4 appears twice, making it the mode. Measures of dispersion tell us how spread out or scattered our data values are from the center. The range is the simplest measure of dispersion. It's the difference between the highest and lowest values in the dataset. This example shows how range works with real data. Group A has weights from 40 to 60 kilograms, giving a range of 20 kilograms. Group B has weights from 10 to 90 kilograms, giving a much larger range of 80 kilograms. Variance measures the average squared deviations from the mean, while standard deviation is the square root of variance, giving us a measure in the same units as our original data. These basic statistical concepts are the foundation for more advanced statistical analysis. Understanding central tendency and dispersion helps us describe and interpret data effectively. The mean, also known as the average, is one of the most fundamental concepts in statistics. It represents the typical or central value of a dataset. The mean gives us a single number that represents what we might expect as a typical value from our data. It's calculated using a simple but powerful formula. The arithmetic mean is calculated using this fundamental formula, the sum of all values divided by the number of values. This formula can be written in several equivalent ways. Let's work through a concrete example. We have the numbers 6, 5, 9, 1, and 2. To find the mean, we first add all these values together. Step 1, we add all the values. 6 plus 5 plus 9 plus 1 plus 2 equals 23. Step 2, we count how many values we have. In this case, we have 5 numbers. Step 3, we divide the sum by the count. 23 divided by 5 equals 4.6. This is our mean value. Sometimes our data is organized into groups or classes with frequencies. For grouped data, we need a slightly different approach to calculate the mean. Here we see a frequency table with grade ranges, their frequencies, and midpoints. For grouped data, we use the midpoint of each class interval and multiply by its frequency. The formula for group data mean is the sum of each midpoint times its frequency divided by the total frequency. This gives us a weighted average that accounts for how often each value range occurs. The mean is crucial in statistics for several reasons. It provides a single representative value for an entire dataset, making it easy to compare different groups. The mean also serves as the foundation for many other statistical calculations and helps us identify the center or typical value in our data, making it an essential tool for data analysis. In essence, the mean transforms a collection of individual numbers into one meaningful value that represents the entire dataset. This makes it one of the most powerful and widely used tools in statistical analysis. The median is a fundamental measure of central tendency that represents the middle value in a dataset. Unlike the mean, the median provides a robust measure that isn't easily affected by extreme values or outliers. The key to finding the median is first ordering our data from smallest to largest. Once ordered, we can identify the middle position. Let's start with an example using an odd number of data points. Consider these test scores: 78, 85, 92, 67, 88. First, we must arrange these values in ascending order from least to greatest. For data sets with an odd number of values, we use the formula median equals the value at position n plus 1 divided by 2. With 5 values, n equals 5. So the median position is 5 plus 1 divided by 2, which equals the third position. The value at the third position is 85. Now let's examine what happens when we have an even number of data points. Consider these 6 test scores: 72, 85, 91, 68, 88, 95. For even-sized datasets, there's no single middle value. Instead, we take the average of the 2 middle values. With 6 values, the 2 middle positions are the third and fourth values, 85 and 88. The median is their average, 85 plus 88, divided by 2 equals 86.5. One of the median's greatest strengths is its resistance to outliers. Unlike the mean, extreme values don't dramatically affect the median. Let's see a practical example. Here we have golf ball distances, and we need to find the median distance. Remember these key points about the median. It requires ordered data, it's the middle value for odd data sets, the average of 2 middle values for even data sets, and it's resistant to outliers. The median's resistance to outliers makes it particularly valuable when analyzing data sets that may contain extreme values, providing a more stable measure of the center than the mean. The mode is a fundamental measure of central tendency that identifies the most frequently occurring value in a dataset. Understanding how to find and interpret the mode is essential for statistical analysis. The mode is defined as the value that appears most frequently in a dataset. It tells us which data point occurs more often than any other. Let's work through a simple example. Consider this dataset: 2, 3, 4, 3, 5, 3, 6, 7, 3. To find the mode, we need to count how many times each value appears. Let's count the frequency of each value. The number 2 appears once, 3 appears 4 times, 4 appears once, 5 appears once, 6 appears once, and 7 appears once. Since the number 3 appears most frequently with 4 occurrences, the mode of this dataset is 3. In visual representations like histograms, the mode is easy to identify as the tallest bar. This represents the value or range of values that occurs most frequently in the dataset. Sometimes a dataset can have 2 modes, called a bimodal distribution. This occurs when 2 different values appear with the same highest frequency. In this histogram, we can see 2 distinct peaks, indicating 2 modes. A dataset can also be multimodal, having 3 or more modes. This happens when 3 or more values occur with the same highest frequency. The graph shows 3 distinct clusters, each representing a different mode. Sometimes a dataset has no mode at all. This occurs when all values appear with equal frequency, meaning no single value is more common than the others. To summarize the key points about mode, it identifies the most frequent value in a dataset. Datasets can have 1, multiple, or no modes, and the mode is particularly useful for analyzing categorical and discrete data. In visual representations, the mode corresponds to the highest peak or tallest bar. Understanding the mode helps us identify patterns in data and is an essential tool for statistical analysis, especially when dealing with categorical variables or when we want to know the most common occurrence in our dataset. Range is one of the simplest measures of data spread or dispersion. It tells us how far apart the highest and lowest values in our dataset are from each other. The range is calculated using a simple formula. Range equals the maximum value minus the minimum value in the dataset. Let's work through a concrete example. Here we have a dataset where we need to find the range. First, we identify the minimum value, which is 64. Then we find the maximum value, which is 95. Finally, we subtract the minimum from the maximum, 95 minus 64 equals 31. So the range of this dataset is 31. Range helps us understand how spread out our data is. Let's compare datasets with different ranges to see this concept in action. Different datasets can have very different ranges. When data points are clustered closely together, we get a small range. When data points are spread far apart, we get a large range. However, range has an important limitation. It's very sensitive to extreme values or outliers. Let's see this with two similar datasets. Dataset A has values from 10 to 15, giving us a range of 5. Dataset B has almost identical values, but one outlier of 50. This single extreme value changes the range dramatically from 5 to 40. Range can be applied to data displayed in various chart formats, as shown here. While range is simple to calculate and gives us a quick sense of data spread, remember its key limitations. Range is easy to calculate and shows us the spread of our data, but it's sensitive to outliers and only uses the two extreme values, ignoring all the data points in between. Understanding these characteristics helps us know when range is useful and when we might need other measures of dispersion for a more complete picture of our data's variability. Variance and standard deviation are crucial statistical measures that tell us how spread out our data points are around the mean. While the mean tells us the center of our data, these measures reveal how much the data varies from that center. Consider these two data sets. Both have the same mean, shown by the teal vertical lines. However, the dataset on the left has low variability with points clustered close to the mean, while the dataset on the right has high variability with points spread far from the mean. The population variance, denoted by sigma squared, measures the average squared deviation from the mean. The formula shows that we take each data value, subtract the population mean, square the result, sum all these squared deviations, and divide by the total number of data values n. Standard deviation is simply the square root of variance. While variance gives us a measure of spread, it's expressed in squared units, which can be difficult to interpret. Standard deviation brings us back to the original units of our data, making it much more meaningful and easier to understand. When working with a sample, rather than the entire population, we use a slightly different formula. Notice that we divide by n-1 instead of n. This adjustment, called Bessel's correction, accounts for the fact that we're estimating the population standard deviation from a sample, providing a more accurate estimate. Here's a simple example with the dataset 2, 4, 6, 8, 10. First, we calculate the mean, which is 6. Then we find how far each value is from the mean, square these deviations, sum them up, and divide by the number of values to get the variance of 8. Finally, taking the square root gives us a standard deviation of approximately 2.83. Standard deviation becomes especially meaningful when we look at normal distributions. This bell curve shows how data is distributed around the mean. About 68% of all data falls within one standard deviation of the mean, 95% falls within 2 standard deviations, and 99.7% falls within 3 standard deviations. This is known as the empirical rule. To summarize, variance and standard deviation are fundamental measures of data variability. Variance gives us the average squared deviation from the mean, while standard deviation, being the square root of variance, provides a more interpretable measure in the original units. Both are essential for understanding how spread out our data is and form the foundation for many advanced statistical concepts. Now we move on to curve fitting, a powerful technique for finding mathematical functions that best represent sets of data points. Curve fitting is the process of finding a mathematical function that best represents a set of data points. Instead of just looking at scattered data, we create a smooth curve that captures the underlying pattern. Here we see scattered data points in black. Curve fitting helps us find a smooth mathematical function, shown in teal, that captures the overall trend in the data. This scatter plot shows real data with a strong positive correlation of 0.89. The red line represents a fitted curve that captures the linear relationship between the variables. Notice how the line passes through the general trend of the data points. Different types of mathematical functions can be used for curve fitting. Linear functions create straight lines, quadratic functions create parabolas, and exponential functions show rapid growth or decay patterns. This diagram shows polynomial curves of increasing complexity fitted to the same data. As the polynomial order m increases from 0 to 9, the red curve becomes more complex. While higher-order polynomials can fit the data points more closely, they may overfit and fail to capture the true underlying pattern. The bottom right plot shows severe overfitting, where the curve passes through every data point but creates an unrealistic wiggly pattern that wouldn't generalize well to new data. Effective curve fitting follows several key principles. We must balance simplicity with accuracy, avoid overfitting to random noise, choose the appropriate curve type for our data, and validate our model with new data points. The first two principles are especially important. Balancing simplicity with accuracy means finding a curve that captures the essential pattern without unnecessary complexity. Avoiding overfitting ensures our model will work well on new, unseen data. Curve fitting is a fundamental tool in data analysis that transforms scattered data points into meaningful mathematical relationships. This enables us to understand patterns, make predictions, and gain insights from our data. Linear regression is one of the most fundamental and widely used techniques in statistics for modeling relationships between variables. It helps us find the best fitting straight line through a set of data points. Imagine we have collected data points from an experiment or observation. These points are scattered on a coordinate plane, and we want to find the straight line that best represents the relationship between our variables. The equation of any straight line can be written in slope-intercept form as y equals mx plus b. This is the foundation of linear regression. In this equation, m represents the slope of the line, which tells us how steep the line is. The value b is the y-intercept, showing where the line crosses the y-axis. The variables x and y represent the coordinates of any point on the line. Linear regression finds the best fitting straight line through our data points. This line minimizes the overall distance between the line and all the data points. The slope tells us how much y increases for every unit increase in x. We calculate slope as rise over run. In this example, when x increases by 4 units, y increases by 4.4 units, giving us a slope of 1.1. The y-intercept is where our line crosses the y-axis, which occurs when x equals 0. In our example, the y-intercept is approximately 0.8. But how do we determine which line is the best fit? We use the least squares method. This technique finds the line that minimizes the sum of the squared distances between each data point and the line. Linear regression is a powerful tool that uses the simple equation y equals mx plus b to model relationships in data. The slope tells us the rate of change, the y-intercept gives us the starting value, and the least squares method ensures we find the optimal line through our data points. The least squares method is a fundamental technique in statistics that helps us find the best fitting line through our data points by minimizing prediction errors. Before we understand the least squares method, we need to understand what we mean by errors or residuals. An error is simply the difference between what we actually observed and what our line predicts. This graph perfectly illustrates the concept of errors in regression. Each blue dot represents an actual data point, while the orange line is our fitted regression line. The vertical lines show the errors, the distances between each observed point and the predicted value on the line. But why do we square the errors instead of just adding them up? There are several important mathematical reasons. First, positive and negative errors would cancel each other out, giving us a misleading total. Second, squaring ensures all errors are positive. Third, it penalizes larger errors more heavily. And finally, it creates a smooth mathematical surface that we can optimize. Here we see the mathematical formula for the sum of squared errors. We take each error, square it, and then sum all these squared errors together. The goal of the least squares method is to find the line parameters that make this sum as small as possible. The least squares method follows a systematic optimization process. We start with any line, calculate the sum of squared errors, then adjust the line's slope and intercept to reduce this sum. We repeat this process until we find the line that produces the minimum possible sum of squared errors. This final visualization shows multiple data points with their residuals clearly marked. Each dashed vertical line represents an error that will be squared and added to our sum. The plus and minus signs indicate whether each point lies above or below the regression line. The least squares method is powerful because it provides us with the mathematically optimal line for our data. By minimizing the sum of squared errors, we ensure that our linear model has the smallest possible prediction errors overall, making it the most accurate representation of the relationship in our data. While linear regression is a powerful tool, many real-world datasets cannot be accurately modeled with a straight line. When data follows curved patterns, we need nonlinear curve-fitting techniques. Linear models have several key limitations. They cannot capture curved relationships in data, they provide poor fits for exponential growth or decay patterns, and they are inadequate for modeling cyclical or periodic behavior. Polynomial regression extends linear regression by fitting curves of different degrees. The degree m determines the complexity of the curve. A degree 0 gives a horizontal line, degree 1 gives a straight line, while higher degrees create increasingly complex curves. As we can see in this comparison, m equals 0 creates a horizontal line, m equals 1 gives us linear regression, m equals 3 produces a cubic curve, and m equals 9 results in a very complex polynomial that closely follows every data point. Beyond polynomials, there are several other important types of nonlinear curves. Exponential curves model growth and decay processes. Logarithmic curves represent diminishing returns or saturation effects. And power curves describe relationships where one variable changes as a power of another. Nonlinear curve fitting presents several challenges. The main challenge is finding the right balance between underfitting and overfitting. Underfitting occurs when our model is too simple and cannot capture the underlying pattern. Overfitting happens when our model is too complex and memorizes random noise instead of learning the true relationship. Additional challenges include increased computational complexity, the presence of multiple local minima in the optimization process, the need for more data to reliably fit complex models, and the critical importance of proper model selection. When choosing between linear and nonlinear models, we should follow systematic guidelines. Start with simple models and gradually increase complexity only when needed. Use cross-validation techniques to assess true performance, and always consider domain knowledge and the need for model interpretability. The key takeaway is that nonlinear curve fitting provides powerful tools for modeling complex relationships in data, but it requires careful consideration of model complexity and proper validation techniques to ensure reliable and meaningful results. Curve fitting involves complex mathematical calculations that can be computationally intensive. Fortunately, modern technology provides us with powerful tools to simplify this process. Manual curve fitting calculations are time-consuming and error-prone, especially for complex models. Technology transforms this process, providing instant results with high precision. This example shows how polynomial complexity increases with degree. As m increases from 0 to 9, the fitting becomes more sophisticated but also more computationally demanding. Software handles these calculations effortlessly. Several categories of tools are available for curve fitting. Graphing calculators offer portability and built-in functions. Excel provides user-friendly interfaces with trendline features. Python offers the most flexibility with powerful libraries like NumPy and SciPy. This Python example demonstrates fitting a Gaussian function to data. The code uses SciPy's curve fit function to automatically determine the best parameters. The blue stars show original data points, while the orange line shows the fitted curve. This example shows how Python's matplotlib creates professional visualizations. The scattered blue points represent original data, while the smooth red curve shows the fitted model. The complete code workflow is visible above the plot. Technology provides numerous advantages for curve fitting. It offers speed with instant calculations, accuracy by minimizing human error, and the ability to handle complex models. Visualization capabilities make results clear, and easy parameter adjustment allows for iterative improvement. Whether using simple graphing calculators or advanced programming languages like Python, technology transforms complex mathematical procedures into accessible, practical tools. This democratizes curve fitting, making sophisticated data analysis available to students, researchers, and professionals across all fields. Correlation is a fundamental statistical concept that measures the strength and direction of the linear relationship between two variables. Understanding correlation helps us identify patterns and make predictions based on data relationships. Correlation tells us two important things about the relationship between variables: the strength of the relationship, which shows how closely the variables are connected, and the direction, which tells us whether the variables tend to increase or decrease together. Here we see a scatter plot showing a strong positive correlation between calories consumed and weight gained. Notice how the data points closely follow the trend line, and the R-squared value of 0.94 indicates a very strong relationship. The correlation coefficient, denoted as R, quantifies the strength and direction of a linear relationship. It always ranges from -1 to +1. Perfect positive correlation occurs when R equals 1, perfect negative correlation when R equals -1, and no linear correlation when R equals 0. These four scatter plots demonstrate different types of relationships. We can see strong linear correlation, curved nonlinear relationships, linear correlation affected by outliers, and cases where there is essentially no correlation between the variables. This scatter plot of height versus average exam score demonstrates a case where there is no meaningful correlation. The data points are scattered randomly with no clear pattern, indicating that a person's height has no linear relationship with their exam performance. To summarize the key points about correlation: first, correlation only measures linear relationships, so curved patterns may not be captured. Second, strong correlation does not imply causation between variables. Third, outliers can significantly affect correlation coefficients. Finally, always create scatter plots to visualize your data before interpreting correlation values. Correlation can move in two different directions. Understanding whether a correlation is positive or negative tells us how two variables relate to each other as they change. A positive correlation means that as one variable increases, the other variable also tends to increase. They move in the same direction together. Here we can see examples of positive correlations. Notice how in the strong positive correlation, the points form an upward trending line. In the weak positive correlation, the points still trend upward, but are more scattered. Common examples of positive correlation include height and weight. Taller people tend to weigh more. Study time and test scores also show positive correlation. More study time generally leads to higher scores. A negative correlation means that as one variable increases, the other variable tends to decrease. They move in opposite directions. Looking at the negative correlation examples, we see downward trending patterns. The strong negative correlation shows points forming a clear downward line, while the weak negative correlation shows a downward trend with more scatter. Examples of negative correlation include price and demand. As prices increase, demand typically decreases. Exercise and body fat percentage also show negative correlation. More exercise generally leads to lower body fat. These scatter plots show different correlation patterns. Notice how some show clear upward trends for positive correlation, while others show downward trends for negative correlation. The strength of the correlation affects how tightly the points cluster around the trend line. The direction of correlation is fundamental to understanding relationships between variables. Positive correlations show variables moving together in the same direction, while negative correlations show them moving in opposite directions. Remember, the direction of correlation is just as important as its strength. Understanding whether a correlation is positive or negative helps us predict how one variable will behave when the other changes. The correlation coefficient R not only tells us the direction of a relationship, but its magnitude reveals the strength of that relationship. Understanding how to interpret these values is crucial for statistical analysis. The correlation coefficient R ranges from -1 to +1. The magnitude or absolute value of r tells us how strong the linear relationship is between two variables. Values close to +1 or -1 indicate strong correlations. The closer to these extremes, the stronger the linear relationship. Values close to 0 indicate weak correlations. Let's look at specific guidelines for interpreting correlation strength. These ranges help us categorize relationships as strong, moderate, or weak. Strong correlations have absolute R values of 0.7 or greater, indicating a very close linear relationship between variables. Moderate correlations range from 0.3 to 0.7 in absolute value, showing a noticeable but not perfect linear relationship. Weak correlations have absolute R values less than 0.3, indicating little to no linear relationship between the variables. Now, let's see what these different correlation strengths look like visually in scatter plots. This diagram shows 4 different scatter plots. The top plots demonstrate strong correlations. Notice how the data points cluster tightly around the trend lines. The bottom plots show weak correlations with much more scattered data points. Here, we can see the difference between strong and weak negative correlations more clearly. In the strong negative correlation, with R approximately -0.9, the points cluster tightly around the downward trend line. In the weak negative correlation, with R around -0.3, the points are much more scattered. Understanding correlation strength helps us determine how reliable our predictions might be and how confident we can be in the relationship between variables. Remember these key points. The magnitude of R indicates strength, with values near 1 showing strong relationships and values near 0 showing weak relationships. Use the standard guidelines and always confirm with visual inspection of your scatter plots. One of the most important concepts in statistics is understanding the difference between correlation and causation. This distinction is crucial for proper data interpretation. Correlation means two variables change together in a predictable pattern. When one increases, the other might increase or decrease consistently. Causation, however, means one variable directly causes changes in another. This is a much stronger relationship that requires evidence beyond just correlation. The fundamental principle is that correlation does not equal causation. Just because two things happen together doesn't mean one causes the other. A major reason correlation doesn't imply causation is the presence of confounding variables. These are hidden factors that influence both variables we're studying. In this example, coffee drinking appears correlated with heart disease. However, smoking is a confounding variable. Smokers tend to drink more coffee, and smoking actually causes heart disease, not the coffee itself. This scatter plot shows a strong correlation between income and rent prices. Areas with higher average incomes tend to have higher rent costs. But does higher income directly cause higher rent? Not necessarily. Both might be influenced by other factors like location desirability, job markets, or housing supply. Here are some classic examples of correlation without causation. Ice cream sales correlate with drowning incidents, but both increase in summer. Shoe size correlates with reading ability in children, but both increase with age. Remember these key points. Always question apparent relationships. Look for confounding variables. Treat correlation as the first step rather than the conclusion. And understand that establishing true causation requires controlled studies and additional evidence. Scatter plots are one of the most powerful tools for visualizing relationships between two variables. They allow us to see patterns, trends, and correlations that might not be obvious from raw data alone. A scatter plot displays pairs of numerical data as points on a coordinate system. Each point represents one observation, with its position determined by the values of two variables. The x-coordinate shows the value of the first variable, while the y-coordinate shows the value of the second variable. The overall pattern of these points reveals the relationship between the variables. Here we see a scatter plot showing a strong positive correlation between calories consumed and weight gained. As one variable increases, the other also increases. The points follow a clear upward trend, and the R-squared value of 0.94 indicates that 94% of the variation in weight gain can be explained by calorie consumption. The trend line helps us visualize this strong linear relationship. Scatter plots can reveal many different types of relationships. This image shows 4 common scenarios we encounter when analyzing data. The top left shows a moderate linear relationship. The top right reveals a curved, nonlinear pattern. The bottom left demonstrates a strong linear relationship with one outlier, while the bottom right shows no meaningful relationship between the variables. Sometimes scatter plots reveal no correlation between variables. This example shows the relationship between chicken eggs on farms and ice cream sales, 2 completely unrelated variables. The points are scattered randomly with no clear pattern. This indicates the variables are independent of each other, and the correlation coefficient would be close to 0. This scatter plot demonstrates a weak negative correlation. As one variable increases, the other tends to decrease, creating a downward trend in the data points. While the relationship exists, it's not very strong, as evidenced by the scattered nature of the points around the general downward trend. The correlation coefficient would be negative, but close to 0. When interpreting scatter plots, follow these key guidelines to extract meaningful insights from your data visualization. First, look for the overall pattern. Then identify the direction of any relationship. Assess how tightly clustered the points are to determine strength. Always check for outliers, and remember that relationships might be nonlinear rather than straight lines. We've covered a comprehensive range of statistical concepts in Chapter 9. Let's summarize the 3 key areas we explored and their most important takeaways. Chapter 9 focused on 3 fundamental areas of statistics. First, we reviewed basic statistical concepts for describing data. Second, we learned curve-fitting techniques for modeling relationships. Third, we explored correlation analysis for measuring how variables relate to each other. Basic statistical concepts provide the foundation for data analysis. We learned to calculate measures of central tendency like mean, median, and mode. We also explored measures of variability, including range and standard deviation, which help us understand how spread out our data is. Curve-fitting techniques allow us to model relationships in data. We learned about linear regression for straight-line relationships and the least squares method for finding the best fit. We also distinguished between best fit lines that minimize overall error and exact fit curves that pass through all data points. Correlation analysis helps us measure relationships between variables. We learned about Pearson's correlation coefficient, which quantifies the strength and direction of linear relationships. We explored positive and negative correlations, and importantly, we emphasized that correlation does not imply causation. These statistical tools form the foundation of data analysis in science, business, and research. Understanding measures of central tendency and variability helps us describe data. Curve-fitting techniques allow us to model and predict relationships. Correlation analysis helps us understand how variables influence each other. Together, these concepts provide powerful methods for extracting insights from data. Let's revisit the fundamental statistical measures that help us describe and understand datasets. We'll review measures of central tendency and dispersion, which are essential tools for data analysis. Measures of central tendency tell us about the center or typical value of a dataset. The mean is the arithmetic average, calculated by summing all values and dividing by the count. The median is the middle value when data is arranged in order. It's less affected by extreme values than the mean. The mode is the value that appears most frequently in the dataset. A dataset can have one mode, multiple modes, or no mode at all. The relationship between mean, median, and mode depends on the shape of the data distribution. In symmetric distributions, all 3 measures coincide, while in skewed distributions they differ. Measures of dispersion tell us how spread out the data values are. Range is the simplest measure, showing the difference between the highest and lowest values. Variance measures how much the data points deviate from the mean on average. It's calculated using squared deviations to avoid negative values canceling out. Standard deviation is the square root of variance and is expressed in the same units as the original data, making it easier to interpret. Here's a practical example of how range works with different data sets. Group A has weights from 40 to 60 kilograms, giving a range of 20. Group B has a much wider spread from 10 to 90 kilograms, resulting in a range of 80. These statistical measures work together to give us a complete understanding of our data. Central tendency tells us about the center, while dispersion tells us about the spread. This combination is essential for proper data analysis and comparison. Understanding these fundamental concepts prepares us for more advanced statistical techniques like curve fitting and correlation analysis, which build upon these basic measures. Curve fitting isn't just a mathematical concept. It's a powerful tool used across many fields to understand patterns, make predictions, and solve real-world problems. Let's explore 3 important applications. Our first example is population growth modeling. Biologists and demographers use curve fitting to understand how populations change over time and predict future growth patterns. Population growth often follows a sigmoid or S-shaped curve. Initially, growth is exponential when resources are abundant. Then it slows as resources become limited, eventually leveling off at the carrying capacity. Scientists use this model to study wildlife populations, bacterial growth in laboratories, and even human population dynamics in cities and countries. Our second application is financial modeling. Investment analysts use curve fitting to identify trends in stock prices and make informed predictions about market behavior. Stock prices can be modeled using various curves. Polynomial regression helps identify trends, while exponential models can capture rapid growth or decline periods. The fitted curve helps analysts identify whether a stock is in an upward trend, experiencing volatility, or showing signs of decline. This information guides investment decisions. Our third application is scientific research. Scientists use curve fitting to analyze experimental data, validate theories, and discover new relationships between variables. For example, in physics, researchers might study how temperature affects the resistance of a material. The relationship often follows an exponential curve that can be modeled mathematically. The fitted curve allows scientists to predict behavior at untested temperatures, validate theoretical models, and understand the underlying physical principles governing the relationship. These examples demonstrate the versatility and power of curve fitting. Whether predicting population growth, analyzing financial markets, or conducting scientific research, curve fitting helps us understand patterns and make informed decisions based on data. Correlation analysis is a powerful statistical tool used across many different fields to understand relationships between variables and make informed decisions. Let's explore how correlation is applied in economics, psychology, and biology. In economics, correlation analysis helps us understand market relationships. One classic example is the relationship between price and quantity demanded for a product. This demand curve shows a strong negative correlation between price and quantity demanded. As prices increase, the quantity that consumers are willing to buy decreases. The correlation coefficient for this relationship is typically around negative 0.8 to negative 0.95, indicating a very strong negative correlation. This information helps businesses set optimal pricing strategies. Now let's examine how correlation is used in psychology to understand human behavior and performance. In psychology, researchers often study the relationship between stress levels and performance. This follows what's known as the Yerkes-Dodson law. This relationship shows a curved pattern where moderate stress levels correlate with optimal performance, but too little or too much stress leads to decreased performance. The correlation coefficient varies depending on which part of the curve we examine. For the ascending portion, R is positive, while for the descending portion, R is negative. This helps psychologists design optimal learning and work environments. Finally, let's explore how correlation analysis is crucial in biology for understanding ecosystem dynamics. In biology, one of the most studied correlations is between predator and prey populations in ecosystems. This relationship demonstrates how species populations influence each other over time. This graph shows the classic predator-prey cycle. The green line represents prey population, while the purple line shows predator population. Notice how the predator population peaks slightly after the prey population peaks. The correlation between these populations is complex. When analyzed with a time lag, the correlation coefficient can be quite strong, typically around zero point 0.7 to zero point 0.9. This understanding helps ecologists manage wildlife populations and predict ecosystem changes. These examples demonstrate how correlation analysis provides valuable insights across diverse fields. By quantifying relationships between variables, researchers and professionals can make data-driven decisions that improve outcomes in business, human behavior, and environmental management. Congratulations on completing Chapter 9. You have now built a comprehensive toolkit of statistical analysis methods that will serve you throughout your academic and professional journey. First, you mastered descriptive statistics, the foundation tools that help us understand and summarize data. You learned to calculate measures of central tendency and variability. Next, you explored curve-fitting techniques that allow you to model relationships in data and make predictions. These powerful methods help you find patterns and trends. Finally, you learned correlation analysis to measure and interpret relationships between variables, understanding both the strength and direction of these connections. These statistical tools form a powerful workflow. You start by collecting data, then describe it using measures of central tendency and spread, identify relationships through correlation, and finally model those relationships to make predictions. Statistical analysis gives you the power to transform raw data into meaningful insights, make evidence-based decisions, identify hidden patterns, and predict future outcomes. These skills are invaluable in virtually every field of study and career. Keep practicing and exploring. Statistics is everywhere around us, in science, business, sports, and daily life. The more you use these skills, the more powerful they become. You now have a solid foundation to continue your journey into the fascinating world of data analysis.